Hello, it's Keith here, and this is lesson 33 of the platform-specific series of my Z80 programming tutorials. Now, we've been looking over the last few weeks at how to do hardware sprites on various systems, but this week I want to do a bit of a change, and we're going to look at the Camputers Lynx. And for the next couple of weeks, we're going to be looking at the Camputers Lynx and how to program it in assembly language. The reason we're going to be covering this system is it was a request by one of my Patreon backers. They suggested I took a look at the Camputers Lynx. I did, and I found it was actually quite surprising in the way it's been designed. And I think it's worth us looking at the Camputers Lynx because the way the Z80 has been used in this system means that it works surprisingly differently to the other Z80 systems we've been looking at. The reason for this is the address bus. Now, of course, the Z80 has a 16-bit address bus, but on the Camputers Lynx, 2 of the bits are completely ignored. The effect of this is that if we write to certain ranges within the standard Z80 address range, we're actually writing to the same bank of memory. The Camputers Lynx is a 48K system, but the memory is split into 2 8KB banks. So Bank A will be accessible from the memory addresses 0 to 1FFF, 2000 to 3FFF, 8000 to 9FFF, and A000 to BFFF. Bank B will be in these ranges here. So the system is 48 kilobytes, but we only have 16 kilobytes for our data memory. Where's the rest of the memory? Well, it's used by the video RAM. If you look at this banking list here, you'll see that there are banks of 8 kilobyte memory for the blue channel, the red channel, the green channel, and something called alt green. Alt green is a page flippable alternate green channel that we can switch in instead of the regular green channel, but there's no blue or red, so it's probably not very useful for most games. So effectively, 2/3 of the memory is actually used by the video, and this makes the Camputers quite powerful video-wise. It's got a 256 pixel widescreen, and the height can go up to 256 pixels as well, just about. And of course, each of the channels is basically a bit plane. So we've got an 8K block for blue, an 8K block for red, and an 8K block for green. And each line is consecutive below the last one, so we can just add 32 to our current position to get the line directly below, which is quite convenient. What isn't so convenient is the way we have to page in the memory. Now, the video memory shares the same address space as the basic RAM, and when we're writing to the video memory, we are in theory writing to the RAM as well, and what we have to do is we have to lock certain banks to make them read only so that we're not corrupting our RAM when we're writing our video memory. So what we have to do when we want to page in the video memory is firstly we need to switch in the banks here with this port quadruple-F, and we have to select the banks we want to write to, and then we have to lock certain areas of the address space using port hexadecimal 80 and writing some bits here. Now, this is all quite confusing, but fortunately it's very easy if you just look at this table. Effectively, if you want to read from the video banks, you need to out this byte to this port here and this byte to this port here, and then if you're looking to use red, then this address range will have the red data. If you're looking to use blue, you use these addresses here. But then if you want to use green and alt green, which are in the alternate bank, you use some different settings just here, and then you use these addresses here. So that's for reading, and for writing we use these settings here. To get things back to the default, we just write 0 to both ports, and everything will be back in the normal way for the memory, with our accessible memory in the range 6000 to 9FFF. Now, as I say, we're having to lock banks as read-only so that we don't accidentally write to them, but we can take advantage of this. We can actually write to the red and green channels at the same time with a single byte written, just by combining these bytes and writing these values to these ports here. And we can also do blue and alt green if we so wished, using these settings here. We're actually going to take advantage of this later, because when we do our font, we're going to write in white, and rather than writing 3 bytes for each of the 3 channels, we only need to write 2 using these options. Unfortunately, because of this limited address space here, when we are accessing our screen, we can't write to our memory, and this has a rather serious implication, because if you think about it, our stack is in memory. So when we're writing to the screen, we can't use our stack in any way, because firstly it would be displayed on the screen and it causes other problems as well. So we're going to work in a way that we don't need the stack. So how are we actually going to use the screen? Well, because we can't use the stack, we're not going to be using any calls to turn on the various ports to get the video memory accessible. So what we're going to do is we're going to define some macros. So we're going to do draw red blue here, because if you look at our chart, red and blue are in the same bank here. And if we want to do green, we're going to use this setting here, because our green channels are in the same bank as well. And then stop drawing is just going to turn everything off back to defaults. So we're going to use these options here, and we've got this all colors one here, which is going to turn on this option here, and this is for our black and white drawing. So let's start by having a look at how we're actually going to draw characters to the screen. Well, it's pretty similar to all of our other tutorials where we've done this. We're going to have an X and Y cursor position, and what we're going to do is we're going to use IY and IX here for the memory addresses. Now we want to write to both memory addresses at the same time because we're wanting to draw white text, so we want to write in this range here and this range here. So we're going to use IY and IX for this purpose, and we need to add the offset of our cursor position to these memory addresses for our correct writing. Now what we need to do next, of course, is work out the position in our 1-bit font where our text is, and then we are going to write the bits from the font to the memory addresses in IX and IY, and we're going to increment them by hexadecimal 20, which is 32, because each line is 32 below the last one. And we're just going to loop for the 8 lines within the font here. Now when we started drawing, we used this screen draw or colors macro, which we just saw defined here, and this will turn on the paging. But once we're done, we use this stop drawing command here, which will also turn off the paging. So that's fairly straightforward, and we're doing a lot of pushes and pops here to protect all of the registers used by here. Now the important thing to notice is while there's a jump, there's no pushes, pops or calls in this, because as I say, we can't use the stack in between this command here and this command here. We're fine using it once we've stopped drawing, because then our memory is back to its normal configuration. So that's how we can draw fonts to the screen, but obviously we want to do things that are a bit more impressive than this. Well, here's an example of how we can draw a bitmap to the screen. You can see I've got my Chibico sprite here as usual, and we've got Vassam says hi at the top, and this is the font code that you just saw me describe. Now this sprite was exported with my AccuSprite editor, which does have a Camputers Lynx export option here. And not only that, but I use my AccuSprite editor for the Camputers Lynx version of my Grime Z80 program, which I've recently released as well. So today we're going to look at how we actually draw this sprite to the screen. Now, of course, the important thing to notice is that the work of actually configuring the data for the computer screen is done by my sprite editor, but we've still got to get the actual data onto the screen. So how do we do that? Well, here's the example code we're doing here. So we use this getScreenPos to calculate the destination location of the bitmap. Then we use this bitmap sprite source data, which is just read in from the disk. And then we've got the width here in bytes. These computers uses 8 pixels per byte because it's bit planed. And so we're using 6 bytes wide, and we're using 48 lines tall. Then we're using this show bitmap command here. Now, this isn't the same version of my bitmap drawing routine as usual, because the Camputers Lynx is very different in the way we need to work. So first of all, let's have a look at that getScreenPos command. And here it is. So we're passing in BC for an XY coordinate here, and it's very simple to calculate the base of the screen. So the basic start of the screen is at A000, and you can see that just here. Of course, we need to add 2000 to move over to the red coordinate later on. And then all we need to do is effectively multiply the Y position by 32, and we do that with a series of rotate rights. We load C into A and rotate it right a few times until it's in the 32 position. Then we add the X position, and that is our destination calculated. So that's pretty straightforward. Now it comes to the show bitmap command, and this is where things get a bit tricky. Now the important thing to notice is once we've used this screen draw red blue, which pages in the red and blue channels, we cannot use the stack at any point after this until we do this stop drawing command here, which I've actually put at the total end of the routine. If your routine was more complicated, you might want to do that every line or even every pixel. But the important thing is we can't do any calls or any pushes and pops in this range here, or we're going to have trouble. So what I'm doing is I'm backing up DE with the IY register here, and I'm using that to then restore them here and here. What we're doing is we're using LDIR commands to copy data from the source data to the destination screen. We're doing this by setting B to 0 here and setting C to IXH, which, if you remember, is the width of the line. So at this point we're copying from the source, which is the data, to the destination, which is the screen, and we're copying IXH number of bytes because we've set the B to 0 here. Now at this point we're doing the blue component, but once we've done that we want to do the red component here. So we need to reset D and E, but then we need to add hexadecimal 2000, and the way I'm doing that is by setting bit 6 and resetting bit 5. But ironically, because of the weird way the Camputers Lynx memory layout kind of overlaps because of that limited address bus, actually we can remove this command and it still works the same, but for clarity reasons I've left it in. So anyway, that's just something to bear in mind. So we're then doing the red component here, and then we need to page in the green component, because if you remember, the green component is in a separate bank setting. So we've paged in the green here, and then we're doing the same again for the green component, but we still need to set bits 6 and 5 here because we are still setting the C000 to D FFF range here. So that's how we're doing it. And then when we get down to here, we're moving on to the next line and we're repeating again. So that's how we are doing our screen. When we get to here, we're finished and we stop drawing. So that's how we can get our Chibico sprite onto the screen like this. But what actually happens if we try and use the stack? Well, let's try unramming this test routine and see what actually happens. Well, there we go. So we're crashing now. So as you can see, because we've got that video memory paged in, it's causing us problems. And also, if I just do some push HLs here, well, you can see we've got corruption at the bottom of the screen here, and that was the actual push commands. But even worse, when we've popped the data back off, we've not got the same data as we just pushed, and so now we're reading in garbage data for our sprite. So as I say, you really need to not use the stack while you've got the screen data paged in. Anyway, that's a simple way that we can access the screen data on the Camputers Lynx. Now, if you're more interested in this, I'd suggest you download the latest version of Grime Z80, because the tile code for that works in 8x8 chunks, and it's a different version of this code. It's been re-optimized, and I made a special exporter in my Sprite editor to export into the correct format for the Camputers Lynx on the 8x8 tiles, so that may be interesting to you as well. Anyway, if you like this video, please like and subscribe as always. We're going to do another lesson next week on the Camputers Lynx. We're going to cover how to use the keyboard and the sound, so please follow me for that if you want to see more Camputers Lynx. Anyway, that's enough for today. Thanks for watching and goodbye.